Anyhow, well, 5.1. Here's the study of how to apply some integrals to real life stuff, real life functions. In 5.1, what we're going to discuss is how to find the area between two curves. It's not difficult. It really isn't. I'll show you that actually we've been doing this the whole time. It's just we had this very special second curve, and I'll show you that right now. So 5.1, we're going to talk about the area between two curves. Here's the idea. Let's say that for some given interval, you have one function that's above another function. So here's our typical, what I always like to draw for my f of x. And here's some other function g of x. Would you agree that according to this graph, f of x is always above g of x for a given interval? And let's define that interval from a to b like we normally do. So from a to b, f of x is completely on top of g of x. Now what we want to talk about is the area between f of x and g of x. That's what we're trying to find. You see, we already know how to find the area under f of x, right? And we know how to find the area under g of x. We're talking about the area between them. How would you go about doing that? Give me some ideas. What would you do? Go ahead.
Find the area of f of x and then subtract the area of g of x.
That might seem logical, right? Because we have this whole area. That's great. That's the area under f of x, true? And this area, which is g of x, well shoot, if I subtract them, aren't I going to get, is that even the way you say that? Aren't I going to get? Sounds right to me, I don't care. Am I not going to get the area between those two curves?
Yes.
I hope so, yeah. It says take this area, subtract that area. It's basically like finding the difference between two numbers, right? You take the large one, subtract out the small one. In this case, we take the upper function. That is definitely going to have more area since it's always above g of x. Subtract the area under g of x, that's going to have less area. We're going to get a positive area. That will be the area between two curves. Let me make this statement for you. If you're finding the area between two curves, it will always be positive. If you have a negative area, you've done something wrong. Okay, your area will be positive. So we're finding an actual definite integral between two curves. You understand the difference between what we're doing before? This is no longer net signed area because of the way we're going to set it up. We're always going to have the top function above the bottom function. We're always going to have more area and getting rid of less area. So we're going to have something that's definitely positive.
What if there?
It'll still work.
Just like on top.
Think about it. Subtract, the function on top would have a negative area. This would have more negative area. You're subtracting more negative area. That would become positive area. Did you get the idea? It's kind of cool. No matter what, it's going to be a positive area. So the idea was, I liked how it was said, take the area under f of x and subtract the area under g of x. That's what we're going to do. No problem. Now, can we do it with integrals? What's the area under f of x represented as? How do you represent the area under f of x as an integral? How would you do it here? Okay. Wait, say it again, add louder. Integral from where to where?
From a to b of f of x dx.
Sure. Hopefully you can see that that's the area under f of x from a to b, right? At least that's what I told you it was, and that's how we've been working with this thing this whole time. So we have the area under f of x, great, minus the area under g of x. What's the area under g of x?
A to b, g of x.
Wait, you're telling me it's the same a to b? Oh, that's cool. So would you say that that's the area under f of x minus the area under g of x, and that's going to give us the area between those two curves? And that's exactly what it's going to give you. Now, why is this so nice? I made a statement just a second ago. You mean it's from the same a to b?
Because the intervals are the same apart.
You could break it apart, but also, what do you know about two integrals that are from a to b and a to b? What can you do with those things?
One and the
Solve them and then subtract.
You could do that. That's one way to do it.
Or you can combine them.
Sometimes it's very much beneficial to combine them. Notice that those were not one-way street properties. They went both ways. Not only could you split up an integral by subtraction and addition, you could also put them together by addition and subtraction, provided they have the same bounds of integration, which this has to have if you're going to find the area between them. So you can do it this way. Do an integral, and find both of them. However, sometimes, not all the time, but sometimes it's nice to put them together because you have like terms. You have common things. You can put them together and do that. So, other way you can see it. Just like that. That's the area between two curves. Just make one big note here. Please make this note. In order for this to work properly, in order for this exact thing to work properly, what do you know about f of x and g of x? The bounds are the same. That has to happen. Very good. Secondly, though,
Non-negative.
say what?
Non-negative.
It is non-negative. It will be positive. Very good. In order for it to be non-negative, though, what do you know about f of x compared to g of x is what I'm trying to get to.
That's to be greater.
What now?
Has to be greater for all x and then.
Sure. F of x must be greater than, or which means on top of. F of x has to be the higher function in order for this to work. Does that make sense? So you have to have your higher function first. Otherwise, you're going to have this reverse situation. You take a bigger area from a smaller area, it's going to end up being negative. You get negative of what you actually want. So in order for this to work, this note says that f of x must be bigger than or equal to, it could come down and touch it, okay? It could do that as long as it maintains the property of being bigger than afterwards. So this is possible. Here's g of x, here's f of x. That could happen. If this is f of x and that's g of x. That would be fine between here and here. F of x is still on top of or equal to, it wouldn't make a difference. Do you follow me on that? The problem, maybe I'll use different colors so you can see it a little better. That would be okay. Perfect. The problem would be this. Why would that be a problem?
Not specific ones above the other.
Okay. So the purple line is on top of the black line here, but the black line is on top of the purple line here. That would be an issue because one of them is not continually above the other one for that whole interval. So for this to work, by the way, this would be the case. This would be, if you just did it the way it was, f of x over g of x, it'd be the case of net signed area. This would be positive, that would be negative, it would cancel it out. Okay, it'd be gone. You get it? So for this to work properly, to get the total area, which is what we're looking for, what you must have is f of x greater than or equal to g of x. For all x in a to b. That little e, that's like an element, says x is a part of that interval. In layman's terms, this says f of x is above g of x for the whole interval. Did you understand the concept that if f of x is not on top of g of x the whole time, if it does this, then this area would be probably positive, but this area would be negative, and it would get rid of some of the positive area that you're looking for. So basically, we're looking for the total area. Notice that we have done this the whole time. We really have. Here's why we've done this the whole time. When I ask you to find the area under a curve, what you've interpreted that as is the area between f of x and what? The x-axis. The equation for the x-axis is
Y equals 0.
Y equals 0.
0. Yeah, y equals 0. So the integral really was a to b of f of x dx. However, think about it. It was really 0. Because that was the second function. We've always been finding the area between two curves. The second curve was just the x-axis. X-axis has an equation of 0, y equals 0. So you were subtracting 0 from it, which is why we didn't show it. Also, this means that when we went below, the x-axis, is why, I gave you that picture just a second ago, is why those areas eliminated each other. Because one is positive, one is negative, because the function flip-flopped what was on top and what was on the bottom. Does that make sense to you? So basically, this would have to be written for total area as this function on top and 0 on the bottom. And then this function on top, and or 0 on top, and the function on the bottom, which is what gave you that negative from the absolute value to begin with. You remember the absolute value? Basically, you could do it this way. If this is C, and this is A, and this is B, wherever that happens to be, you could go, okay, from A to C of f of x minus 0 plus C to B of 0 minus f of x. Yes, no? That says keep the top function on the top. Here's the top from A to C, f of x, minus 0 for the x-axis. Here is from C to B, great. 0's on the top, the function's on the bottom. Notice how what this actually does here is gives you this relationship that we got exactly the same thing from absolute value, exactly the same thing. This gave you some integral f of x. Look what would happen. 0 minus f of x is negative. Pull out the negative, minus C to B f of x dx. It subtracted the negative area, making it a positive area. It changed the sign on it. And that's what absolute value would do as well. Do you see the connection between the absolute value, way we did that for total area, and now the idea of area between two curves? Do you see the connection? If you don't, that's okay, but I need to know. Are there questions on it? So absolute value said, hey, just take the area and make it positive. Great. That works the same way. But area between two curves says, hey, think of it as two curves. Think of this as one curve, but think of the x-axis as another curve. Then the area between two curves becomes the idea of total area. It says you take this function on top of that function for this interval, no problem. And you add to it this function, 0, on top of this function for this interval. And that's going to make it positive. That's going to come up with total area the same exact way. So area of two curves and total area are the same. Do you see it now? That's kind of cool, right? So now we have two ways to approach that. I would suggest that this is probably the easier way to approach that if you know the x-intercept. That's probably easier than absolute value because you have to think of that. But either way is not too difficult. Now, we have done no examples. Would you like one? All right. Did you understand everything we've talked about so far? Yeah? Are there questions so far? You're allowed to ask questions, I promise. I won't get too mad at you. Not even mad, not even a little. Fine.
It makes sense. There's not going to be word problems on these,
I love the disdain with which you asked that.
are there? Word
There's not going to be word problems, are there? They're all word problems. They have words in them and problems. We're going to start off nice and simply. I'll give you some very easy ones to accomplish, and after that we'll have more work involved in them. So I want to start you off just basic, okay? So most of your homework will not look like this. Some of the ones that are like on the first part it'll just give you a picture and say, hey, this one's on top, this one's on bottom. Then I'm going to show you a way to find out which function is actually on top. So in this, I'm going to say find the area bounded above, which tells you the function above, and bounded below, which tells you the function below, on a certain interval. Very easy to set up. That's the one the pictures are going to give you on the homework. They're easy to set up. They're not bad. So we're going to do one of those, and then I'll show you how to do something a little bit more advanced. So find the area bounded above. By that function. And bounded below by this function on a given interval. They got to give you an interval, or you have to be able to find one. On 0, 2. You know, sometimes for these, if they don't tell you what's bounded above or bounded below, it's nice to draw a picture. Get the idea. See which one's above, which one's below. You don't have to, absolutely, because I'm going to give you a way to do this without having to draw a single picture. But sometimes it helps just to make sure you see it in your head. You with me on that? You're, okay, now I can see which one's above and which one's below. That's nicer. But you don't have to. Well, hey, let's try to set it up. All we need to know for this is where you start, where you stop, and which one's on top. That's basically it. So area between two curves says, hey, where do you start? Come on.
It's trying 0, 2.
0. Where you end?
2.
What function is on the top? When it says bounded above, it means for the whole interval. When it says bounded below, it means for the whole interval. If it doesn't say bounded above or below, we would find those regions, and we'd be able to determine that. So bounded above by 2x plus 5. Do I add or subtract?
Subtract.
Yeah, you're subtracting. Remember, you're basically taking big area minus small area to find the area between them. Also, I'm going to show you something here that I don't want you to neglect. Some of you are infamous, I guess would be the word, for neglecting parentheses. Notice that parentheses, not in this case, but in some cases will be very important because that sign will distribute if there was more than one term. Do you follow me on that? If I gave you x cubed plus 1, for instance, there's a huge difference between this integral and that integral. Do you see it? The sign would definitely change. So I'd like you to practice putting parentheses, just saying, hey, this is my top function, this is my bottom function. Then if the parentheses don't do anything, so what? You erase them. But at least you don't forget them. You got me? Because that would be so horrible to understand this concept, which you seem to, and be able to set the problem up, which you seem to, and then get the wrong answer. That's the worst kind of ignorance. Oh my gosh, being able to do something and not following through and getting it right, that's the worst. Because it's not even ignorance, right? It's just failure to perform. No one likes that. So parentheses in this case aren't doing anything. We got 2x plus 5 minus x cubed dx. Notice how we don't have to have two separate integrals. When we put them together like this, it just basically becomes one large integral, which is great. We could easily do that. It's just subtracting off this piece of the puzzle. Can you do the integral? Go for it. Go for it. Do the integral, evaluate it. You know how to do this. Remember that what I'm teaching you now is really not anything new. It's just an application of the process. Application of integrals to find an area between two curves. The next problem is one you can expect on a test, this coming test, as it were. Something like the next one. So we'll do this one, be prepared. This is kind of an easier example that I'm giving you. It's very easy to set up, it's all given to you, and you can do it very quickly. That one has a little bit more setup, and we'll talk about that in a bit. So doing your integral here, hopefully you were able to come up with which is what I'm going to do, 2x squared over 2 plus 5x, don't forget about that 5x, minus x to the 4th over 4. Yes, no? Now, of course, the 2, we can simplify that. So x squared plus 5x, looks a little funny, plus 5x minus x to the 4th over 4. And we're going to evaluate from 0 to 2. There's nice, there's no substitution that we needed. We can just go for a direct plugging in some numbers. So our area is, we'll plug in the 2. Subtract. When we plug in 0, we are going to get 0. I'm just going to show it so we don't forget it. Don't forget to plug in 0, because sometimes if you do have some constant in there, especially with the substitution, it won't be 0. But make sure you make a note of that. So in our case, our area is going to give you, how much is all that? How much?
18.
18? More people got 18? 10. Oh, let's see. 4, 10, and 4. 10. Watch the negative. That subtracts 4. Show of hands, how many feel okay with this so far? Cool deal. Now, would you like to try a problem that's a little bit more robust? This is pretty basic. Pretty basic. Hopefully we're all okay with that one. Now, something that's not as basic is find the area bound by, or another way to say that is find the area between these two curves. I'm going to give you some steps on how to do that. Follow these steps to the letter. They will walk you through every problem, okay? Follow the steps. When it's like this, very easy. You set up from the problem. When it's like this, follow the steps. Here's the step. And a sketch does help. If you have a graphing calculator, sometimes that does help. Plug it in, find out which one's on top. But I'll show you how to do it without a graphing calculator, of course. First one. You know, before you can find the area between two curves, you got to find where those curves intersect. Do you notice I didn't give you a range? I didn't give you from 0 to 2 or from something to something. That means that this is going to be completely enclosed between some boundary of our curves. When that happens, when I don't give you an interval, you need to be able to find the interval. Now, fortunately, it's just based on the x-intercepts, because that's how our integrals work. From x equals whatever to x equals whatever, from A to B. So, step number 1 is find the x-coordinates of where your curves intersect. Okay, tell me, how do we find the x-coordinates of the intersection of our curves? What would you do for that? Say what?
We're going to take y equals 0.
Equals 0? Not quite, you're close. How do you find out where two curves cross?
Or the y intercept.
If you set them equal, you find out where they are equal, right? Where they actually intersect. So, how you do this, set the curves equal to each other. Not 0, but to each other. I'll do it that way. Set f of x equal to g of x. Whatever your first function is, equal to your second function. Because right now, just off the top of your head, do you know which one of these is on top of the other one? Because I don't, just by, I can probably figure it out by doing a little math. But right now, just looking at it, it doesn't say it explicitly, does it? It doesn't say, hey, this one's on top. It doesn't say that anywhere. So we're going to have to do a little work, and this is kind of an easier example, but most of the time, you're going to look at it and go, I don't know. You're going to have to do what I'm telling you to do. So take the two functions, set them equal to each other. So go ahead and do that now. Why don't you try to solve it? Get in the habit of doing that again. We haven't done stuff like that in a while. Here's what I mean by set them equal. You take your x squared in this case, set it equal to x plus 6 in this case. No problem. Can you solve it?
Yes.
I sure hope so. I sure hope so. This goes back to your algebra days, right? Whenever you see a quadratic, you always get things to one side and you solve with quadratic formula or you factor. Typically factoring is the best way to go. You rarely want to complete the square, it takes too long. And if you can't factor, you use quadratic formula. So that's how you complete quadratic. So in our case, we have x squared minus x minus 6 equals 0. Yes, no? Hopefully. Factoring is pretty basic in this one. You're going to have x minus 3 and x plus 2. That means x minus 3 equals 0. X plus 2 equals 0. Stop me if I make a mistake, by the way. You're allowed to do that. 3 and negative 2. How many other people got down to that far? Okay, so your algebra still checks out, right? Hey, guess what you have right now?
Your bounds.
Got your bounds. Got your bounds integration. Where do your bounds start? Where do they stop? So automatically you have this. You know your integral starts at negative 2 and ends at 3. Because that's where they intersect. That's where your areas are going to start and stop. That's going to be enclosed in that graph. You got to figure, if your graphs intersect at 2 spots, here and here, and they're continuous, there will be at least some area between them, unless they're exactly the same curve, which they won't be, otherwise they'd have an infinite number of intersections, right? So they're going to have some area between them. Now, it could do this, like it could go, there could be lots of areas, but it will have at least some. Now, if there were more than just one, there'd be more numbers here. Wherever they intersect would give you another range of an integral, another bounds of integration. So this just has one range. It's from negative 2 to 3. That means we'll only get one integral. Are you with me on this? So I'll say it again because some of you, I lost you. I can see it in your eyes. Listen, when you set two functions equal to each other, you find the only places that they will intersect. You believe me? If they intersect at 2 spots, there's only one region between there. If they intersected at 3 spots, there'd be 2 regions between there. If they intersected at 4 spots, there'd be 3 regions between there that you would have to calculate. Did you get it? And it might alternate which is on top and which is on the bottom. Here, we only need to figure out, for this one interval, which is on the top and which is on the bottom. So that brings us to step 2. Determine which is on the top. Which function is on top? How would you do that? How would you do that? Say what? Kind of maybe overthinking it just a little bit. Let's go back to this. Where's your integral start? Where's your integral stop? Would you agree that for that interval, one function will necessarily be on the top of another? For sure. It will not cross, because if it crossed, folks would have another intersection, right? It starts here, it stops there. One's on top, one's on the bottom. You got me? So, if one's on the top, one's on the bottom, for this interval, tell me how you find out which one's bigger than the other one. Plug in a number, man. Plug in a number. Whatever number you want, provided it is within here. You don't want to plug in -3 or like 7. That would be a little silly. Plug in a number on your interval, and it's going to tell you which function's on the top very quickly. So, which function's on the top? How are you going to do this? Pick one point on each interval to plug in. There's only one interval here, so we only have to plug in one point. Step number 3, you're almost done. It's going to be the setup and solve of the integral. But let's go ahead and I'm going to show you how to do this. We already know this is going to be the case. I'm going to not complete this integral until we go over here. This is just like a starting point for us. I want to have -3 to 2. That's my interval. I know that one's going to be on the top, one's going to be on the bottom. So we're going to take a number and we're going to plug it in. Oh, I am reversed. My bad. I'm glad some of you have very good confused faces. Otherwise, I'd be at a loss of what you know. So be like, wait a second. You can't pull that one on. I'm just testing you. You passed. Yeah. You don't buy that, do you? We're going to test a point. What's a good point to test between -2 and 3?
0.
Clearly. Plug in 0. So we'll do y equals x squared. And maybe we'll do down here. You can see a little better. Y equals x squared. Y equals x plus 6. You said we're going to test 0. You're going to test 0. This is not too hard to test. You're just going to plug in a number and see what the number is. So plug in 0, y would equal 0. Plug in 0, y would equal, which one is on the top?
Y equals 6.
Wait, y equals what?
Y equals 6. Y equals x plus 6.
Okay, so for your interval, this is a nice little graphic organizer. It says, what's going to go on the top? Ah, x plus 6. What's going to go on the bottom?
X squared.
Very good. Do you feel okay on getting the x plus 6s on the top of the interval, to the top of the graph, I suppose, for the interval, and then x squared is on the bottom of the graph for the interval? That helps you set it up, doesn't it? Isn't this kind of like a picture of your integral right here? It says you start at -2, you go to 3. This is on the top, this is on the bottom. Set it up, subtract them, and you're good to go. But you're going to feel okay with our idea here, the idea behind it. Are there any questions before we actually set up the integral and do it? Okay, well, let's go for it then. Okay, so our area, we already knew that it's going from let me mess that up again, -2 to 3. We now know which function's on the top. It's the x plus 6, so that's going to go first. I'm going to get in the habit of putting parentheses around it. That way, if I have to distribute anything, I know my signs are correct. Minus, not plus, but minus. We're subtracting big area minus small area. If we know what's on top, then that's set up perfectly for us. Minus what now? Don't forget your dx. Now, of course, those parentheses don't do much for us in this case. It just was a way to organize and say, here's my first function on the top, here's my second function on the bottom, and then subtract them whatever they happen to be. So our integral goes from -2 to 3 of x plus 6 minus x squared dx. You okay with that one? Go for it. Why don't you find out how much area we got? The basic hard part is over with. It's finding out where you start, where you stop, and which one's on top. That's the hard part. The integral, you already know. You've mastered integrals. You know how to do it. At least I hope you've mastered integrals. That homework's going to tell me right now, right? By the way, as I'm thinking about it right now, before you get going, notice that if they say find the area that's bound by a function and the x-axis, you would do exactly the same thing, only the second function will just be 0. Remember how we talked about that earlier today? So you just have to do the same thing. Just set the function equal to 0 and solve it, find out where it's on top, where it's on the bottom. It's the same idea. this.
Where's that 3 times 3?
Oh, it should be 6. That's 2 today. I must have a case of the Mondays. Darn it! I hate Mondays.
Okay.
Oh, I just made a mistake, that's all.
Two cubed, not 2 squared, in your lower boundary function. You have negative 2 squared divided by 2.
Yeah.
That's right. Oh, sorry, I was reading it backwards.
Now you make me doubt myself, Joe. Come on now.
No.
You're killing me. I think that's right.
It is.
I'm going about it. Help me out with some fractions there.
Yeah, I came up with 125 over 6.
Yes. By show of hands, how many people also came up with 125 over 6? Let me ask you this question. Were you okay down to at least here? Okay, good. That's the calculus. After that, make sure you're putting the numbers in right. Watch your signs. Signs are a real pain when you're doing this. Especially the -2. I mean, you got to really be careful with that. Pretty sure I did that right. That should be 54 plus 40. No, I'm wrong.
81 plus
Yeah, 81 and 44. That's right. Are you ready to try another one, or are there any questions on that one? You feeling good about it? Feel like you know how to handle these type of problems so far? Are you seeing the similarity between what we've done already and what we're doing now? The integrals are exactly the same. We're still finding areas. It's just now I'm giving you 2 curves to start with, but look, it makes the same type of integral.
Setup's harder, but the
Setup is harder.
Yeah.
The setup takes a little more work.
motion's the same.
Mm-hmm. Now, let's go ahead and find the area bound by y equals x cubed and y equals x. Have I given you any bounds of integration here?
Why was it? No.
Bounds of integration. So where you start and where you stop on the x-axis. Do you know that yet?
Not yet.
That clues you in on what to do first then. What are you going to do first?
Determine the intersection.
Okay, very good. Now, notice something. If I gave you a problem, this is going to be very too simplistic for you, but just watch. If I gave you this, bound by the x-axis
Did we just do it normally?
and that, this would be y equals 0. In this case, you could still follow the steps. You could still follow the steps. You'd have, well, it wouldn't be bound though, that would be a problem. How about, 0, 1. Like that. If I asked you to do that, find the area bound by the x-axis and that curve. How you would start it out is you would do the same thing. Set the curves equal to each other. Just like that. See what I'm talking about? Yes, no?
Yeah.
And then you'd solve it. X minus 2 equals 0, x would equal 0, and x would equal 2. And in that case, well, it's going to do the same thing as absolute value would do for you. You'd set up your interval from 0 to 2, and you'd plug in a number. Plug in the number 1 to 0. It's 0. Plug in the number 1 to this. It's... Almost fell asleep. You guys ready? Are you with me so far? So you have 2 functions, right? Y equals 0 and y equals x squared minus 2x. If you plug in 1, y still equals 0. If you plug in 1, well, you get y equals 1 minus 2, you get negative 1. Which one's on the top?
Y equals 0.
0. Which one's on the bottom? Do you see what it's going to do? Here's what your integral is going to be set up as. Your integral would be 0 to 2, 0 minus x squared minus 2x, in parentheses, because that's going to change that sign in the back end. How many people were able to follow that one? Now, I went above and beyond, all right? That was just giving you something a little extra. That wasn't even our problem, but I wanted to make sure you saw it at least once. That way you're like, what's that x-axis mean? What's that mean? It means 0. Do the same exact thing. Find out which one's on the top. If the 0's on the top, basically it's just going to make it negative. It says that your area was below the x-axis, and making it negative is going to make it positive. Negative, negative equals positive. That's what that's doing for you. Now let's go back to our original problem. It's not going to take us long to set it up, so we'll finish it today, and then we'll start on something a little bit different next time. So what did I give you anyway?
X cubed, y equals x cubed, and then y equals x.
Not y cubed.
Wait,
How about that?
Yeah, that's what it was.
Okay, if I don't give you bounds, again, you got to find your bounds. Find your bounds by setting those things equal to each other. That's step number 1.
That was the last problem. So you should go x cubed equals x.
Yes, no?
Yep.
Okay. Have you already solved it?
Yeah.
So solve it by subtracting the x. You're going to get x cubed minus x equals 0. Factor it, of course. You're going to get x times x squared minus 1. Keep going. 0.
Or x equals 0.
X plus 1. X minus 1. You get how many points? 1, 2, 3, 4.
3.
Don't forget about that one. X equals 0. X equals 1. X equals negative 1. I think I have those out of order, but those are the 3 points that you get. Raise your hand if you're able to find those 3 points. Feel okay with that? Now, when you set this up, where's our ultimate interval? Where does it start? No, where does it start? Where's it end? Notice how what you did, you found the only 3 points in the world where these things actually touch, right? You found the only points in the world where they could actually have bounded some area together. So negative 1 starts it, 1 ends it, but there's a point in the middle where it could change. Remember the graph I gave you at the very beginning of class where the colors switched? That's might be what we have happening right here. So you got to check for that. So it needs to include that point 0. And how many intervals are we actually going to test? 2 intervals typically means 2 integrals. 3 intervals means 3 integrals. 4 means 4. 1 means 1. So this means we're probably going to have an integral here, and we'll probably have a different integral here with just our functions reversed, depending on which one is on the top and which one is on the bottom. So for each interval, test a point in both. What point do you want to test over here? And over here, probably 1/2. If I'm testing negative 1/2, y equals x cubed, when I plug in that negative 1/2, it's going to give me negative 1/8. If I test this in the y equals x, it's going to give me, well, this is pretty easy, negative 1/2. Now, think carefully, which one's on the top?
X cubed.
This one's actually bigger than that number, right?
Yeah.
It's bigger. So this one is on the top, x cubed and x. Do you see how this picture shows you how to set it up? It's kind of nice. I would encourage you to use that. You don't have to, but without drawing a graph, that's a really nice way to do it. You go, okay, it starts here, ends there, that one's on the top, that one's on the bottom. You see why the x cubed is on the top? You plug in any number in here, this low point's going to equal 0. That one's always going to be bigger than that one. Now the 1/2. When I plug in 1/2, this will be 1/8. And this will be 1/2. Which one's bigger here? X. Very good. So x is here, x cubed is there. We're going to do the setup and then we'll end there because I'm pretty sure that you can do this on your own, but stick with me for the setup at least. So let's do our setup, make sure it's right before we go. We're going to have, how many integrals do we have? So it's basically like a two-part problem here. We're going to have one integral from -1 to 0. That's where it starts and stops. Which function is coming first here?
X to the third,
And then what?
then minus x,
Very good.
dx.
I would typically be putting parentheses around those things, but because they're only single terms each, we can kind of neglect that. We just have x cubed minus the x. Nod your head if you're okay with that so far. Okay. What are we going to do now?
We're gonna add,
Are we going to add or subtract?
we're combining the two.
We're basically wanting to say the area here and the area here, right? I don't want to subtract them. I want to add them. I'm doing two different problems right now. And they have to be done differently because the order changes. Top and bottom change. You have to have twice. So big old plus. Another integral. Where's the integral start?
0 to 1.
0 to 1 of what?
X minus
Now, just because this goes from -1 to 0 and this one goes from 0 to 1, you can't combine them because they're not exactly the same function. So you have to do two different integrals. Do this one, figure out what it is, and then we'll start here. We'll probably start here next time. I'll just start with this integral, I'll give you the answer, and that will be our game. All right, so we're on this problem. Let's finish it up. We're basically down to the part where we're just evaluating the integrals, which is going to stand for the area. I think the way we did this was we realized that we need to separate any interval into how many segments you have, find out which functions on the top, which functions on the bottom for each interval, and then make up basically one integral per interval. So if you look at last time on the video, or you look at your notes from last time, the way we set this up is we had x cubed on top of x between -1 and 0, and then another interval went from 0 to 1, but x was on top of x cubed. So that's where these setups come from, at least for finding area between two curves. Now, as far as accomplishing the integrals, let's see if we got them right. So we got x to the 4th over 4 minus x squared over 2, and we'll be evaluating that from -1 to 0. And then we'll have another integral giving us x squared over 2 minus x to the 4th over 4 from 0 to 1. Now, unfortunately, I think I said this last time, but I said it as we were leaving. Unfortunately, there's no way to put those together to make one integral out of it, even though the bounds match up. They really do. -1 to 0 and then 0 to 1. Because our functions are not the same, we can't do that. Feel all right with that so far? Okay. So let's go ahead and accomplish this one. And plug in all of these numbers. 0 over 4 minus 0 over 2 minus -1 to the 4th over 4 minus -1 squared over 2, and make sure you have that in parentheses. It's important to have that because that sign's going to change. This is basically this first one. That's what that is. Then we're going to add to it a whole other one. We'll plug in our 1. Subtract off our 0. Fortunately for us, our 0 doesn't do anything. But I still want to show it because I don't want to lose it in case it did do something. A substitution, sometimes you'll still plug in 0 and you'll still have a number after that. How many people made it that far, by the way? On that. Cool deal. Now we'll work through this and try to get some proper answers. This is going to give you 0. This gives you 1/4 minus 1/2, and it's in parentheses still. Plus. This gives you 1/2 minus 1/4 minus 0. Are we still okay so far? All right, very good. What you're going to get out of that, hopefully you're going to get -1/4. Did you get -1/4? That's going to change it to +1/4. So this segment is 1/4. plus this is going to be altogether you have, aha, how many were able to find area 1/2? Which is kind of cool when you think about it. We're able to find now the area between two curves when one of the curves isn't the x-axis. We talked about that last time, right? Basically, we're doing the same thing, finding the area between two curves where one of them was the x-axis. Now we're saying, what if it's not? What if it's some other curve? It's not that big of a difference. All we have to do is make sure we know where those curves intersect. That sets up each of our integrals, then find out which function is on the top for each of those curves. Raise your hand if you feel okay with what we've talked about so far. All right. Now, I want to show you a couple applications and another way to think of this concept. So basically, I'll show you an application and I'll show you one example that we're going to do two different ways. One way is going to be the way we've done. One way is going to be significantly easier. You ready for it? Rock on. Let's do this thing. So here's an application. I want you to see this. Do you guys like racing? Like cars and stuff? I love racing cars. Personally, watching it, whatever, I'll race anything. I love doing that. So anyway, let's talk about racing cars, and to keep it simple, we're going to do this. You pull up next to me at a red light, and then the light turns green, and right as it does, because my reflexes are freaking awesome, I gun it. And I'm way ahead of you, because my car is fast and I'm awesome. So naturally, that's going to happen. Unless you drive a motorcycle, you're probably not going to beat me in my car. So let's say we do that. Here's what's going to happen. We're going to compare our time to our velocity. Where do we start? If we're at a dead stop, we're starting at 0. Both of us are starting at 0. And my velocity goes like this. I hit my little peak, right? And then I switch gears or something, and then I go, that's me. This is me. And here's you. Okay, that's you. Sorry, but my car is awesome. I'm going to win that race every time. Notice that what these things are, this is a function of our velocities according to time. At time 0, we're at a dead stop. Time 1, I'm going very fast and you're not fast yet. Anyway, I don't know what car you have. I'm just making a joke anyway. But these are our velocities. This is velocity 1, or velocity me. And this is velocity u, 2.
That is the technical term.
Sure. My question is, between here where we start and here where the race is over, let's do that. A or 0, and B where the race is over, do we have any area between the curves?
Yeah.
The question is, what does that area actually represent? Clearly I won. Right? Clearly I won, because my velocity was quicker than yours. This is not position, by the way. This is not position. What this would be, if you had a position curve, or if you have a velocity curve, you could integrate to find your position. Remember that? Velocity to position, you integrate. Or if you had a position curve, you could actually find the derivative to give you velocity. Make sense? So you could get this, and this might be the function of a slope of a position curve. That's what this is. So these are velocities. Now, tell me something. We're finding area, right? Area. What's the width? Time. What's the height? What's time times velocity?
Distance.
You ever seen that before? Distance equals rate times time, right? That is an area. Basically what you're doing in these, think back to what you're actually doing. What you're actually doing here is finding little rectangles, right? And adding them all up. A little rectangle would be a little piece of time times a little piece of velocity. Time times velocity is a distance. So what this area represents is the distance that I beat you. The distance at the end of this, the distance between my car and your car. Do you get the idea? That's kind of cool. So given two velocity curves, we can figure out not only who won the race, but how much they won the race by. That's neat. You can't do that if you just compare the velocities. Like at the end of the time, say, oh, I was going 120, you were going 105. Well, who won? Well, probably I won because I'm going faster. How much did I win by? I don't know that. You could say seconds, right? You could say you won by 4 seconds. Does it say where you were and where I was when I won? No. But this does. This says if I were to find the area between them, the area between the two curves, so notice here, this could be a velocity. Area is velocity times time. That gives you a distance. So the area between the two curves is representing a distance between my cars. In this case, the area equals the distance that car 1, me, is in front of you. In this case, the area represents the distance car me is ahead of car you. How would you find the distance? How would you find that area?
By running our same, I think we've been doing.
Okay, how specifically would you do it?
You would subtract car U.
Just subtract them?
No, I'm trying to think of how to word it.
How would you do it? Come on. How would you find an area between two curves? Set it up. Where does it start? Where does it start? A, or in our case, if we're a dead stop.
0.
0.
Where's it end? Yeah, wherever that time was. In our case, B is going to be time after 20 seconds or whatever. Say, how far am I ahead of you after 20 seconds? That's what this would do for you. What's going to come first? V sub 1t or V sub 2t? Explain why. Definitely. Notice that this was kind of a simplistic example. Sometimes cars go like this, right? They start off and you have an automatic and I have a stick shift. So probably I'm ahead of you, and then if we have very equal cars, I'm going to shift and you're going to keep going with the automatic, you know? So we might go back and forth and back and forth. You'd have to set up several integrals to figure that one out. You get me? Every time we crossed back and forth, that interval would be a different integral. That would give you the overall distance between the two cars as we went. Now, if you wanted to figure out another sub-point here, figure out the total amount of time that, the total distance at the end that I'm ahead of you, that would be net change. You'd have to just do one integral. If you want to find total distance as we went, as like a cumulative effect of how much our cars were apart, whether I was in front or whether you were in front, that's where you'd have all those different integrals. Does that make sense? The area between the curves would represent the overall distance that we were apart the whole length of time. Net integral, where you just went from, no matter what happened here, from from A to B or 0 to B, that's going to say at the end of the game who was ahead. That's what that would do. You get the difference there? So it's kind of a fine point, but it's kind of an important one. That's what you do. So basically the same idea. So right now we could think of these things as distances if we really want to, if we're racing cars. It's kind of cool. I just want to throw that in there because I love racing cars. That's kind of interesting. Now, let's do one more example because I want to show you a couple ways to think about this. Do you have any questions on that before we get going? I'm guessing your silence says no. No? All right. Okay, you might not like this example so much, but it's good for you to see it because you're going to get something like this on your homework. So stick with me. Even if you don't like it, stick with me. Not bad. difficult, maybe, to understand at first. After at first, it's not bad. Okay, why don't you like the example so much?
Because it's solve for y.
It's not even a function in terms of x, is it? It's actually a function in terms of y, not in terms of x, combined with the function that is in terms of x. So that right there goes, oh gosh. Do we have to have functions? Not necessarily. Not if we can break them up in some manner, which is what we're going to do for the first method of doing this. Secondly, I don't tell you much about this. I don't say where you start, I don't say where you stop, I just say do it. So, we need to find out where integrals start and stop, right? Okay.
Right across.
One thing is probably you're going to want to find the intersections because that's going to give you at least some range. Also, a picture would be very, very helpful here. Very helpful. We're going to draw a picture first so that you can have a graphic representation of this. And generally, you don't need a picture as long as you really understand the curves. One thing I'm telling you about is this. If you just do the intersections of the curves, when you don't have functions in terms of x, you can miss key points. For instance, on the x equals y squared, do you know what that is?
What's the square root of x?
Okay, not just the square root of x though. You remember when you take square root, you have to have plus or minus. It's actually a parabola on its side. Do you see the parabola on its side? What that means is that our curve is probably going to intersect here and here, which is what it's going to do. We'd be missing that point. That point right there is going to be x equals 0, the start of your parabola, right? So even though the function does not intersect right there, that is a key point because on the x-axis, that's where we're starting. So that's a key one. So you need to see things like that as well. That's what makes this problem difficult. Let's draw the graphs first. That way we can really get a picture of it. I'll explain everything that I just talked about. Okay, first one, x equals y squared. If x equals y squared, that means that x is a function of y. That means that basically you do this. You take your graph and you go, and you look at it sideways. So if we look at it sideways, this thing is actually a parabola. You okay with that one so far? Yes, no?
Yes.
The other function is pretty easy. The other function is a line. Y equals x minus 2. Can you graph that on the same set of axes? Okay, let's go ahead and do that. Y equals x minus 2 says the y-intercept is where, ladies and gentlemen? Where? And the slope is?
101.
Those are our two functions. Would you agree? Does it have bounded some area within it? Now, let's go ahead and try to focus on where that area, what that area is. First thing you're going to notice, if I find my intersection points, does it tell us where to start and where to stop?
Doesn't tell you where to start.
Is it going to miss some, it's going to miss some area. Do you see that? It's going to miss a lot of area. Because starting would start here and end here. That's a problem. We actually have to start here, which is where the picture comes in nicely, or really understanding your graphs. You really have to know what they look like. You have to know where that thing starts. Hey, I know because I've done this stuff before. I know that's starting at x equals 0. I know it. And it's facing this way. So I know that that integral has to start at x equals 0. I know it's going to end somewhere, but I know it's starting right there. Does that make sense? And the picture illustrates it very nicely for you, but at least you have to have that picture in your head before you even contemplate this problem. Now, the next thing I told you was, okay, follow the steps down. Follow step 1, which is set these things equal to each other and solve them. Okay, set them equal. How are we going to set them equal to each other?
Have to solve for y.
You could solve for y. That's going to be a little difficult because you're going to have square root plus and minus for x, right?
Solve for x.
Maybe solving for x would be the better idea. So step number 1 says, all right, I have x equals y squared. I also have y equals x minus 2. And I want to find some way to set those things equal. Now, solving for y, again, might not be the best bet because you'd have to take a square root with a plus and minus. That's difficult to do. Other way you could do it, well, this is already solved for x, isn't it? This one's not hard to solve for x. How would you solve that for x? So I would say x equals y plus 2. I reversed them on you, but x equals y plus 2. Now you have to be okay with that so far. Well, now that I have x equals y squared and x equals y plus 2, what do you know? Can you make a different equation out of that? Can you solve? Yeah, very easy. How would you solve it? Come on, tell me.
Just factor it.
The idea is to get everything on one side and then factor it, yes. It is a quadratic after all. It's in terms of y, but it's a quadratic. And hope that it factors. Really, honestly, hope that it factors.
If it doesn't.
It's kind of a pain if it doesn't, it really is. Y minus 2 and y plus 1 is what I got out of that. Did you get that as well? That means that y minus 2 equals 0 and y plus 1 equals 0. You're going to get y equals 2, y equals negative 1. By show of hands, how many feel okay with what we've done so far? Okay, true or false? Our integral is going to involve the numbers negative 1 and 2.
Yeah.
Okay. Okay.
Those are bounds,
Well, that's my question.
right? One of them is a bound, and one of them isn't.
Okay, I'll give you that 0 is going to be one of my bounds, yeah? 0. Is 2 and negative 1 other bounds?
And negative 1 is your y-axis bound going downwards, and then you have your 2 would be your bounds on your x-axis going to the right.
Okay, so that's my question,
So
actually.
you could have an integral into y.
Well, that's my question. What are you integrating with respect to? The x-axis or the y-axis? The answer is either one, but you have to make a choice. Okay, either one, but you have to make a choice. I'm going to show you two ways to do this. The first way is saying, I'm going to integrate the way we've always done it with the x-axis. In this case, these numbers really are only there to get you x values, to tell you where your integrals start and stop. That's it. This isn't good enough if we're going to integrate this way. So if we're integrating this way, it says, hey, look, I basically have 3 different functions I'm talking about. 3 of them. Check it out. If I'm talking about functions this way, I think of this as, oh my gosh, well, if I solve this one, x equals y squared, if I do solve that for y, I get plus or minus the square root of x equals y. Do you follow me on that? This right here, because look, if you're going to integrate, you have to have functions in terms of x. You have to. If you're going to integrate x's, you've got to have functions that work. You can't say I'm plugging in one number, get 2 things out. You got to say, here's one curve and here's the other one. Does that make sense? You can't treat it as one big function of x because it's not a function of x. What it is a square root of x here and a negative square root of x there. Can you follow that one? You sure? No?
I got lost there. I understand where the 2 formulas, the 2 different functions come from.
This one and this one?
I'm not sure I'm following the ramifications of that.
Okay. Ramifications are, you have to go ahead, you have to be able to integrate some way. If we're talking about integrating with respect to x, you have to have functions in terms of x. Unfortunately, there's no way to represent this as a single function of x. It's not a single function of x. It is actually 2 functions of x. One on the top and one on the bottom. Have I lost you yet? Gone over your head? By blowing your minds up like a grenade? Wow, that's great. A little bit. It should be. Just stretch your minds. Not too far though, because that'd be freaky. Big heads walking out of here.
Green Lantern.
Creepy. Anyhow, do you see how I'm getting the square root of x and the negative square root of x? We have to break it up into functions of x. So this has to be written in terms of x in order for you to integrate it with respect to x. So you can't have y's in there if you're integrating with respect to x. You get me now? Can you hear me now? Good. So I'm breaking that and saying, hey, x equals y squared. No. Take a square root. involve the plus and minus, and you get plus or minus the square root of x. Plus the square root of x, minus the square root of x.
So those are two separate functions.
Yes, very good. Square root of x and negative square root of x. Those are two functions in terms of x, and then a third one, y equals x minus 2. That's another function of x. So how many do we have all together? 3. 1, 2, 3. 3 functions in terms of x. The problem is, we are in terms of x. What variable did you solve for? Can you go and change these into x's using what you know though?
Yeah.
Okay, let's do that. So for y equals 2, x equals what? For y equals negative 1, x equals what?
4 and 1.
How'd you get 4 and 1?
X equals y squared. I was looking
Yeah.
at 2 and that equals 4. Do the same thing with negative 1 and that equals 1.
Perfect. Exactly right.
You can do it with the other problem and you get the exact same answer.
You could. You could do it from right here as well, correct? So either one of these things, if I plug in y equals 2, hey, x is 4. Plug in y equals negative 1, hey, x is 1. You get me on that? Do it here even, like he said. If I plug in 2, I get 4. If I plug in negative 1, I get 1. It has to work, because you said them equal. That has to be the case. How many will feel okay on getting the x bounds? Now, what I'm going to do is change my graph just a little bit. I'm going to erase the parts that I don't need, because it looks a little confusing to me right now. This part is not binding any area, if you want to say it that way. Neither is this part. Neither is this one. Neither is that one. If you don't mind, I'm going to redraw this picture a little bit bigger so you can see it. Would you be okay with that? Okay, it's clearly not the scale, but it's the same idea. You see the curve I'm trying to draw here. Let's think about what we actually have going on. Remember, we are talking in terms of x, What's this top function from 0 to whatever this point is?
Square root of x.
What's this piece right here?
Negative square root of x.
What's this piece right here?
X plus x minus 2.
Yeah, very good. Now tell me the points. Where does my functions start?
At 0.
Good, 0. We saw that actually basically from the picture. Or understand that's a parabola that starts y-shaped, really going this way, a function of y, but starts at 0. Hey, what's that point? What's this point? We found out they intersect at 1 and, no, 1 and 4 on the x-axis. That's where these numbers are coming back at. The y's said they intersect at negative 1. Ha, look at that. And 2 on the y-axis. Yes, that's true. We don't care about y in this context if we're dealing in functions of x. We care about x's. That's why we had to find the x's. Now, if you're okay with that. The y's would have given us something completely different if we did it this way with y values. Wouldn't have happened. This goes 1, 4. Sure. Now I've kind of given this away by this picture. How many integrals do you need here?
3.
Explain 2. Why 2? Right. 2. Why 2?
0 to 1 to 4.
0 to 1, 1 to 4, but why?
Oh, you have 2 intersection points only.
We have 2 intersection points.
You explained that yesterday, that however many intersection points you have, you're going to have the integral.
Okay, so how many, if you consider this as 3 functions, how many intersection points do we have?
2.
Not 2. I'm holding it up. Yeah. if you consider this as 3 functions, look, you have 2 functions, that's 1. There's 2, there's 3. Yeah, you have 3 functions. Joe, you were going to say something.
I thought maybe you're gonna add the areas from the square root of x to x minus 2 and then negative square root of x to x minus 2, something like that.
We're going to deal with this as just 2 basic areas, but I want you to see, you're kind of missing something. You're kind of missing something. Think about it this way. I'll try to lead you to the answer. The way integrals work for areas is one function is on top the entire time, and one function is on the bottom the entire time. We have 3 functions. So, can one function be on the top the entire time and one function be on the bottom the entire time? That would only be 2 functions. My question is, do you switch functions somewhere? Yes. Where do you switch functions? So basically, look at it. You have to deal with the top and the bottom, right? You have to have the same function for that whole interval. So the same function goes to the entire top. That's great. However, right here, I clearly change functions. That necessitates 2 different integrals because I don't even have the same function. Do you get the idea? So here's the setup for us. Setup for us goes, and hopefully you can see, I want you to help me here. Integral. Where does the first integral start? Very good. Where's the first integral end? Good, because that's the intersection. That's where I'm trading off my 2 functions. In fact, if you did it this way, and you did what I told you, and you had 0, 1, and 4, you'd see it. You'd see it. You'd say, oh, look at that. Square root of x is on the top. Negative square root of x is on the bottom. Do you see it? And then you did it here. Which is on the top for this range? Square root of x is on the top. What's on the bottom? Oh, not negative square root of x, but what? Yeah, and that shows it. I swore, I gave you everything you need to know. I really did. It's right here. You just need to realize what's going on. So 0 to, make it a little clearer. Negative square root of x. 0 to where? Of what?
Square root of x minus a negative square root of x.
Square root of x minus, because you subtract top one minus bottom. What's the bottom one?
Negative square root of x.
Don't lose that negative, otherwise your integral goes to 0. We don't want that to happen. Minus that,
dx plus.
for sure, dx. Would you agree that that integral represents this little area right here?
No.
Big old plus
0.
1, what now?
1 to 4.
0 to 1, 1 to 4, sure.
I wrote 1 to 4. I just think it through.
It's all right. What's in the top now?
Okay.
The table does it if you want to do it that way. I love the table. I just made it up. Like this last class. Cool, huh? Square root of x minus what?
Parentheses.
Oh, parentheses are pretty important here. Dx. Sure, absolutely. Can you do those 2 integrals? Before you do them, be smart about it. Simplify what you can. Okay, don't start just taking random integrals before you start simplifying and putting things together. That would be a silly way to go. You definitely don't want to start dealing with this with all the parentheses. You don't want to start dealing with that until you combine like terms, which you do actually have here. So let's go ahead kind of nice and slowly and think about what we're doing. We got an integral from 0 to 1. We got a square root of x minus a negative square root of x. How much is that?
2.
Hey, that makes things easier already. 2 root x. Plus another integral from 1 to 4. Square root of x minus x plus 2. You see where the plus 2 is coming from? That's a big deal. Dx. Let's keep it going here. We're on a roll. 0 to 1. How are you going to write that integral?
2 x to the 1/2.
X to the 1/2. Very good, because then you can use our integration table and do that. Probably also, you might want to be pulling that 2 out, just for fun.
Oh, well,
You don't have to.
Yeah, so it can leave in there.
You can. You can surely leave it inside of there. That's really just a personal preference. The next one I'll have from 1 to 4, but I'll have x to the 1/2 minus x plus 2 dx. Oh, x to the 1/2. Don't forget we're adding and dividing. 3/2 over 3/2. So when we're setting it, I've not put my integration or my evaluation symbols up there yet. I want to simplify it first, but remember that this is from 0 to 1. And this is from 1 to 4. So before I plug anything in, I'll move the 2 up to the numerator. That's going to be 4x to the 3/2 over 3. Now we're going from 0 to 1. Plus, this is going to be 2 x to the 3/2 over 3 minus x squared over 2 plus 2x from 1 to 4. By show of hands, how many have made it down that far? Hey, the rest of it's just evaluation. Plug some numbers in. Let's see if we can do it. I'd like for you to hopefully do it on your own. Stop me if I make mistakes, by the way. If I'm doing something wrong. Say what? Where? Here? Am I still okay? I think so. Keep going, keep going. I want to say that's 13/6 from right here. Did you make it down that far, just to make sure I'm doing it right? Okay. And then all said and done when you're, let's see, multiply by 2, 32, 8, 40, 53 over 6? No.
55 over 6. That's what I got.
Really? 51 over 6? Make sure I'm good up to here.
I got 4 thirds,
4/3, 16/3,
16 thirds.
minus 13/6.
Minus 13/6.
Okay, multiply by 2, that's 32, multiply by 2, that's 8, 32 and 8 is 40, 27/6 is what I'm getting. Okay, I need to know how many people got 27/6. Let's have like a quadruple, a quintuple check, or whatever. 27/6, 27/6, 27/6? I hope not, hopefully you reduce that as well.
Minus
9 halves perhaps?
Yeah.
13. That's why I count with 9 halves.
Just making sure.
You're thinking 27/6.
Well, before we reduce, yeah, 27/6.
Okay, because I
Yeah,
get.
3 is a common factor. Let's go back down to our, to get that, 9 halves. Do you see the 9 halves?
Yes.
Do you feel okay with our example?
Yes.
By the way, this is the worst possible way you could do this problem. The worst. Why? This is very hard. This is very hard to split that up. In general, hard to do. Easy for this one, hard to do in general. It's have 2 different integrals. Now, what I want you to do is face the board. Turn your head like this. Seriously. Are you doing it? Yeah. Turn your head like this. Is there one function that's on top of the other function when you're doing this? That means you can do it easier with respect to y than you could with respect to x. I'm dizzy now. Seriously, I am. Let's think about this for a second. I might go a couple minutes over today, but you need to see it because we're going to finish this up. So my apologies. It will not take very long. Here's an idea for you. Sometimes you can switch the roles of x and y. Let's suppose you had 2 functions. Now, of course, these functions are going to be in terms of y, not in terms of x. So we'll start with something like x equals h of y. X equals g of y. Like that. It will be going not according to the x. Don't care about the x. Care about the y. It will be going from C to D. And the area we're talking about is that area. Notice that if you put your head like this, right takes the place of top, left takes the place of bottom, but we still go from C to D. It's basically like taking this picture and doing this with it. Like reflecting it across white, almost like reflecting across white, almost.
Is that G of y?
Yes. Our area in this case would be, where would it start on the y-axis? Where does it start for here?
C.
C. Where's it end?
D.
Which one's going to come first?
Oh,
Which one's on the top or on right?
X equals h of y.
So it'd be h of y
Minus.
minus g of y d what? dy. In terms of y now. In terms of y. So basically, h of x is to the right. H of x is to the right. And this, of course, is if h of y is greater than or equal to g of y for all of c to d. Guys, this says the same thing I said for this type of thing. It just says in terms of y instead of terms of x. Let's go ahead and let's do this setup on our problem over here. I will show you it will be basically very easy.
Or did the same one as before?
Same one. Yeah, I want you to see that this works out the same. Now, if we're in terms of y, I need you to notice something. That this, we had this. We had x equals y squared, and we had y equals x minus 2. You with me? If we're going to do this in terms of y, our functions need to be in terms of y. Now, this one's great. We love this one. This one's not great. Explain to me why.
It's in terms of x.
It's not. How do I solve it for terms of y? those would be the two functions I'm comparing. If you set them equal to each other, I'm going quickly through this because this is exactly what we've done before. You're going to get the same exact points that we did before. Y equals 2 and negative 1. Are you still okay with that? Honestly, raise your hand if you feel all right with that. Cool. So now that we have these functions in y, we have y squared here. We have y plus 2 here. Is there one function that's completely, not on top of, but to the right of? If you turn your head like this, it would be on top of. And we have one function that's on the top or on the right of another function. Okay? Now, from this way, where does it start? Where does it start? Where's my integral start? It goes from bottom to top. Where's my integral start? Where's my integral end?
2.
So my area is from negative 1 to 2. Notice that's from C to D, negative 1 to 2. That's why I had my y's. It's in terms of y. Negative 1 to 2. The function on the right was y plus 2. The function on the left was y squared dy. Yes, no? Feel okay with it so
Basically,
far?
just use the y-axis as we would the x.
You're exactly doing that.
So you just turn it and makes it easy.
Kind of, but you can't go from left to right, you're going from bottom to top, so that is wrong. You can't go from 2 to negative 1, you have to go from negative 1 to 2. So you can't just turn your paper. That doesn't work for your bounds. It works for your functions, doesn't work for your bounds. So be careful with that. Did you see the point, what I'm trying to make there? Why is this nicer? Hey, how many integrals? One integral. One integral. If you do the integral, parentheses really don't mean much here. You're going to get y squared over 2 plus 2y minus y cubed over 3, and you evaluate it from negative 1 to 2. If we do that, work it out, but you're going to get exactly the same answer. You plug in your 2, whatever you get there, you plug in your 2, you plug in negative 1, you subtract them, you are going to get 9 pounds.
Yeah.
Easier? Yeah, it is. It is easier because we have one function over one function in terms of y, but we didn't have that in terms of x. So sometimes it would behoove you to really look at your function before you get started. You follow me on this? How many people understood that example, feel okay with it? So can you switch your variables and deal with this in terms of y then in terms of x? Absolutely. Just be careful. Be careful with your bounds especially. If we're solving for functions in y, have your y variables. If you're doing it in terms of x, have your x variables. Plug them in accordingly and you should have no problem.